Excellent, thanks. First of all, thank you for the opportunity to give this talk, and thank you for accommodating my last-minute request because of my travel. So today I will talk, as you already mentioned, about observation of topological polaritons in metasurface integrating two-dimensional transition metal decalcagenide. So this is collaborative work between us, the City College of New York, and the ITMO University and the University of Sheffield. So I'm not sure. I'm sure there were several talks about topological photonics, probably not necessarily in this session. So, but let me briefly mention that, of course, we are motivated by condensed matter topology, which revolutionized our understanding of states of matter. And this is just first theoretical overview, a historical overview of how things evolved over time. So everyone is familiar, of course, with the most influential works in this field by von Klitzing and later by Kane and Melle, who theoretically extended this concept of topology to systems with preserved time reversal symmetry. So what I'll be showing today essentially is reproducing one step which also reproduces this transition from system with broken time reversal symmetry, which have been demonstrated in topological polaritonic systems, to the case of system with preserved time reversal symmetry in photonic topological systems integrating transition metal decalcagenides. Of course, what we are looking for are the same benefits which topology offers us, is robust and spin polarized transport, which can be reflectionless. And this is our goal, to demonstrate this in polaritonic systems. Okay, so a few words about topological order on photons, because we are largely following work in condensed matter physics. Our approach to topology and photonics are also very similar. And basically, there are two main ways we can achieve topology for photons. One is by breaking time reversal symmetry, which in photonics means using either magneto-optical materials, or in the context of polaritonics, having electron gas, let's say two-dimensional electron gas and quantum wells in the presence of magnetic field, and coupled strongly to photonic modes, which yields to topological photon polaritons. So in our case, we will try to use a different approach where we don't have to break time reversal symmetry. So it will be time reversal invariant system where we use symmetry induced pseudospin to emulate quantum spin Hall effect of condensed matter physics. So, of course, again, the advantage of using time reversal invariant system is that we don't need strong magnetic field. We avoid using magnetic materials, which in photonics we typically try to avoid this because magnetic materials and strong magnetic fields are not necessarily very friendly to photonic application systems for practical devices, integrated silicon photonic devices, and so on. So we are therefore motivated to explore options without external magnetic field. So, but the benefits that we gain in the systems with time reversal symmetry are similar, as long as our symmetries, which are responsible for a pseudospin and for the symmetry protected topological phases, are preserved, which we can ensure due to high quality of fabrication, nanofabrication in our systems. We have gained the same benefits we obtained topologically robust H transport, which is spin or pseudospin polarized in our case, because we don't talk about real spin, we talk about this pseudospin generated by typically the latest symmetry of photonic crystals. So, photonics community widely explored these two approaches based on broken time reversal symmetry. Sometimes time reversal symmetry breaking is replaced with modulation in time, which is known as Flaquet topological insulator. So you can see some works that I just give here as an overview of topological photonics, which exploit the breaking of time reversal symmetry of Flaquet topological phases. And our approach is based on time reversals, preserving time reversal symmetry, and instead using symmetries of the structures, which can be either lattice symmetries of the photonic crystals, or this can be some hidden symmetries of electromagnetic field, which we can restore in our metamaterials, such as electromagnetic duality, and so on. So if you are interested, you can just look at all these previous works, including our work in HM materials, where we introduced a symmetry protected topological phase, where the symmetry responsible for topological order is electromagnetic duality. Okay, so today I will use a different approach, which relies on lattice symmetry, and the design that we'll use was originally introduced by Hafizi group. Oops, sorry. You can see these two works. The first theoretical work was published in New Journal of Physics, where Barik and co-authors have demonstrated that if we consider graphene lattice of triangles, as shown here, and we so this would be our graphene unit cell, and then we instead of having two atoms per unit cell, we start to distort this lattice by bringing these triangles closer to one another or farther apart. We in fact obtain two new lattices. In the case of expansion, when this is the upper hexagon shows the new unit cell, we obtain the topologically non-trivial photonic system with topological photonic band gap open, and this topological photonic band gap was shown to host topological edge states on its boundary. So if we shrink our hexamers and we obtain this lower unit cell, and again we open the photonic band gap because we reduce the symmetry of the crystal, but in this case the band gap is trivial. So what Hafizi proposed to have interface between two such structures, and this solved the problem of the leakage of this mode, which is very significant issue, of course, for photonics, because light tends to escape from interfaces due to radiative leakage, especially if we start to bend or if we have some defects on the boundary. So in the case, if we have two such systems, topological and trivial, then immediately we have two overlapping band gaps, and we obtain H transport along the topological domain wall formed by the interface between these two structures. So, so here, of course, we want to move forward and add extra degrees of freedom offered by transition metal decal KHANIKAEVs, more specifically excitonic degrees of freedom. This is our goal. Another thing that actually we want to be able to see this mode in radiation. So you can see here that this topological band gap actually appears near gamma point, which is obviously above the light cone, and therefore this mode should be radiative. But in the case of Barik, their goal was actually to avoid leakage and to ensure propagation for as far of the mode as long as possible. So in our case, we want actually to use leakage to characterize the modes and to use Fourier plane, backfocal plane imaging to visualize topological boundary states. For this reason, we adjust the design a little bit. So we also make sure that shrinkage and expansion, so this distortion of the original graphene lattice is larger, which makes band gap wider and makes our modes more radiative and easy to detect in the far field spectroscopy. So we previously have done that in a different design, the same concept of the spin hole photonic insulator. So where we have clearly seen that we can outcouple topological bulk modes and topological boundary modes, right? And we can see the band inversion of the modes, so where we can clearly see that the modes which are dipole and quadrupolar, they have very distinct radiative coupling, and therefore they appear as either low quality spectrally broad modes or very narrow quadrupolar modes which are weakly radiating into the continuum. So so motivation, of course, to explore polaritonics, in our case exciton polaritons, is the fact that we couple matter excitation with light, which envisions completely new phenomena not available in photonics. For example, exploring some quantum phenomena. Of course, the uttermost goal would be some observation of Bose-Einstein condensation in topological polaritonic systems, enhanced nonlinear effects. For example, potentially observing solitons, topological boundary modes, which would be nonlinear and robust, and maybe polaritonic lasers. So many reasons to really look into this direction. And of course, I should acknowledge a significant work which was done by many groups in both theory and more recently experimentally realized in a quantum well system. So here I will give you some more recent, update on the what's really was done recently. So the original works proposing theoretically the concept of topological polaritonics date back to 2015, and only recently experimentally it was shown that two-dimensional quantum wells patterned on the nanoscale to form photonic crystals can support topological exciton polaritons, and topologically robust H transport has been demonstrated. So why I'm citing here only one work, although I mentioned there was a significant, of course, contribution, numerous experimental works. The thing is that most of those demonstrations actually have shown one-dimensional, quasi-one-dimensional topological polaritonic phases. So, but if we talk about true two-dimensional topological systems characterized by chair number, in this case, to the best of my knowledge, this experimental work is the only work which demonstrated such topological order. Okay, so here, however, again, this demonstration relied on the use of external magnetic field. You can see the magnetic field was very large, 5 Tesla, which again makes this system not very practical for photonics applications, right? And this is why we really want to move away from breaking time versal symmetry and from the use of magnetic field to magnetic materials. So here you can see the idea that we propose to implement topological exciton polaritons with time versal symmetry. So we propose to use two-dimensional semiconductors, transition metal dichalcogenides. In particular, we'll use molybdenum diselenide. And we know that this material has very large in-plane dipole polarizability, which allows relatively easy to achieve strong coupling between photonic and excitonic degrees of freedom in heterostructures. So what we do, we place transition metal dichalcogenides on top of our topological metasurface, which is designed also to be of high quality factor photonic modes, and which would again enable the strong coupling. And our theoretical results indeed show that in such systems we can achieve strong coupling, and I will talk more about the emergence of topological exciton polaritonic H states. So, so what really happens when we couple
You have turned off your microphone.
Sorry, probably accidentally. Can you hear me now? Yeah, probably.
Yes.
It just happened, right? So I shouldn't go back. Did it just happen?
Just continue, please.
Okay, thank you. So here, what really happens when we couple 2D material with photonic topological system? So this is the system. Again, we start with the system proposed by Barik, and we explore what happens if we place a transition metal decalcagenide on top of the system. So you can see that if the original system here, I'm talking about now a topological system which characterized by spin chain numbers of, let's say, for a particular spin up, which indicated by sign plus here. For lower band, it's equal to 1. For upper band, it's -1. So, excitonic band, its spectral position is indicated by this dotted line. So now if we turn on coupling between the two, what we observe that indicates a strong coupling, the band gap occurs here, and actually the topological charge is transferred from photonic band. So we form lower polaritonic band and upper polaritonic band, and now the topological charge is transferred completely on the upper polaritonic band. So, of course, provided the chain number is not 0, the system is topological, and it should obey bulk boundary correspondence principle. But before moving to the edge physics, so let's look at really what happens. Of course, you can say this is kind of quite intuitive, that topological charge, it cannot disappear, it cannot be really destroyed by the interaction with excitons. So, but still we want to see what happens effectively, how our upper polariton obtains topologically non-trivial character. So here you can see effective Hamiltonian describing our system. So we have photonic part, excitonic part, and the interaction part, which of course should take into account all the degrees of freedom, internal degrees of freedom responsible for the topology. So this is not just coupling of two scalar states. These are vector states with a complex internal structure. For example, the photonic Hamiltonian alone is described by well-known Bernevik-Hughes-Zhang Hamiltonian here, where 2 degrees of freedom corresponds actually to photonic value degree of freedom, and 2 correspond to the polarization of light, or we can call it photon spin. And then, of course, excitons, we also know that they have in-plane polarizability. So effectively, we can say we have circular left and circular right excitons, which are also linked directly to value degree of freedom of electrons in transition metal decalcagenides. Therefore, the coupling actually also has this form. It's not a scalar coupling between scalar bands. So now, of course, the topology sits completely in the photonic part of the Hamiltonian. So, but we know that actually, if we want to find the eigenstates of this Hamiltonian, we need to diagonalize, and this is typical eigenstates for any Dirac-like Hamiltonians, right? So this is this eigenstates. So what really happens to our effective coupling with between photons and excitons if we move to this basis of new states, right? And we use the states to diagonalize this photonic part of the Hamiltonian. So what happens actually if you apply this transformation to our photon-exciton coupling term, what we obtain is this new effective coupling. And we see that this effective coupling acquires, because again, just the structure of this photonic topological eigenmodes, right, which have binding in them, right, so that they have Berry phase. So this Berry phase is actually, it's getting transferred to this effective coupling between photonic and excitonic band. And this is an important ingredient for topological excitons, polaritons, which has been known and reported in some previous works. But here, what we show that in fact, you have two of such phase winding, because again, we emulate spin Hall effect. We have two types of excitons, which are effectively spin up and spin down, which are time reversal partners of one another. So we have two of such windings, which have, of course, opposite phase winding with respect to one another. Okay, so and it's indeed then become clear that this phase winding is responsible for really the transfer of the topological charge from the former photonic band to the new upper polaritonic band. Okay, so now, of course, if our upper polaritonic band is topologically non-trivial, the bulk boundary correspondence principle should stand. If we consider an interface between trivial and topological systems, we should observe band crossing topological boundary modes at the interface. So, and you can see this is numerical calculations for our system. So this is our band gap, which is formed between lower and upper polaritons. You can see in here, in both cases, this is a complete band gap. So lower band is topologically trivial, but the upper one, upper polariton, is topologically non-trivial. And we see that indeed band crossing states appear in the topological band gap. So we consider two scenarios. In one scenario, it's kind of obvious why topology is present for upper polaritonic band. For this case, we position our exciton, or more precisely, we can say we position our photonic band, topological photonic band, such that exciton crosses it deep inside. And then, of course, in the case of strong coupling, we open this band gap between upper and lower polaritons. And then it's obvious that, of course, for topological photonic system, most of the Berry curvature appears here at the tip of the photonic band. So it's in some sense, it's clear why the topological charge is still present and this band is topologically non-trivial. So more interesting situation is when we place exciton right exactly at the tip of the former photonic band. In that case, we observe the similar situation. We open a complete band gap between upper and lower polaritons, right? This is the strong coupling regime. It should be that way. And again, we see the edge states. However, what is important? Of course, we cannot expect our hybrid polaritonic bands to be highly excitonic, right? So question is to what degree they're excitonic, because we are interested in these modes having as strong excitonic component as possible. And it appears that in the second scenario, this topological boundary modes appear much more excitonic. You can see the degree of excitonic component from 0% to 100% is shown by the color. So you can see that for this case, the second scenario, even at the mid gap at this Dirac point, probably it's not correct to call it Dirac point, but this crossing of the forward and backward boundary modes, the polaritonic band appear to be up to 20% excitonic, which is
2 minutes.
Yes. So here I'll briefly now mention what we have done to observe the states. We fabricated the structures. We transferred molybdenum diselenide encapsulated into HBN, and then when measuring the backfocal plane imaging from the samples, we observe the photonic topological bands with the edge modes, and more importantly, what we see that topological boundary modes, they asymptotically approach our upper polaritons, which clearly indicates that this is the upper polariton really carries non-zero topological charge, in this case spin chair number. So we also demonstrated one-way propagation of our topological exciton polaritons by exciting modes at the boundary by circularly polarized light. You can see here unidirectional character of these modes. For left circle polarized modes, we only see modes with the excitons, polaritons with positive group velocity. For opposite hand, it's negative group velocity. And by fitting this experimental data. Again, we want to figure out to what degree these modes are excitonic. You can see here that for the first case, when the excitonic band is deep inside the photonic band, it's not that excitonic, but it still carries up to 5% of excitonic component. On the other hand, if we match excitons with the tip of the photonic band, then again, as I mentioned already, up to 20% in the mid gap, H states can be excitonic. So therefore, this demonstrates that we can have highly excitonic topological boundary modes, which are pseudo-spin polarized and also potentially carry Valley polarization. Okay, so now here and conclude. So photonics in general offers an ideal platform for emulating topological states of condensed metaphysics and for controlling light with synthetic gauge field, but adding condensed meta components such as excitons, for example, gives much more opportunities, for example, to explore nonlinear phenomena, some quantum phenomena, and even tunability in our work, which is available on arXiv. We demonstrated actually temperature dependence of topological boundary modes and temperature-induced topological transitions. So here I would like to thank you again for the opportunity to give this talk, and thank you for your attention.
Thank you very much. Thank you very much for this beautiful presentation. We have time for discussion. Questions, please. And first question goes from Dmitry Solnyshkov.
Well, yes, thank you indeed for this very interesting talk. I understood one important thing for me, that actually when you said about this fabrication imperfections, that you have really a very good quality structure, and the topological protection that you need, it's not against small defects or, for example, scattering into excitons, which non-radiative excitons, which are at high wave vector at the same energy. It's rather scattering against the interface which makes a turn, something like this. Yes? Is it
right?
true?
Absolutely right. Yeah. It's
well, okay. But then my question is actually about the excitonic fraction. I wanted to discuss a little bit more.
Sure.
Because you have two types of experimental figures, and some of them, well, seem to have Rabi, which is rather small. So you can say, well, here, for example, the middle of the gap is really far from, with respect to the Rabi splitting, it looks to be very far from the, so it looks like the exciton fraction should be really small. But then you say that it's 20%. So
no, here it's not 20%. Here it's about 5%. Here it's about 20%. So
okay, so indeed these are different structures.
Sorry.
Different structures or what?
Yeah. These are different structures. So two scenarios that I have shown. In one case, so the exciton cuts the topological photonic band deep inside. So it's kind of not very deep, but far away from the tip. So in that case, excitonic component is not that significant. I mean, it's 5%. What do we count as significant or not? But if we instead, like in this case, we have photonic band, let me draw this photonic band, and excitonic band touches it right at the tip. So we have strong coupling, like in this way. So in this case, excitons bends upward, photonic band bends downward, if we can say that. So then we form this upper polaritons, which are the bulk bands themselves, they are highly excitonic at the tip. And this is why, of course, it ensures the high excitonic component of the boundary modes.
Okay, thank you very much. Thanks.
Okay, thank you. Next question comes from Teng Tan, please.
Hi, Professor. Thank you for your nice talk. I think this winding coupling stuff is quite interesting. Actually, we happen to have a very similar paper appearing in Science like recently. I think currently it's expressed online, and I think we have a bit different theory model from your model. So basically, I think the difference is that to account for the spatial variation of the field,
Right.
We actually also expand the excitonic band into these D bands and the P bands. So
right. So of course I know. I was reading this paper, right? So the thing is, what you observe is the strong coupling between topological photonic boundary modes and the excitons, right? So I don't think you demonstrate that your excitons are really topological, right? What you see, the hybridization of topological photonic band edge mode, right? Topological photonic edge mode with excitons, right? Which is of course very nice result. I'm not saying anything, but you're right, it's different, right? So what we do instead, we hybridize bulk mode, right? And we show that this effective phase winding makes our bulk excitonic mode topological. So this I can say two different approaches, and what we have shown that you can just couple photonic boundary modes, which are topological, to
no, actually we also couple the bulk mode, but with a slightly different model. So actually I'd like to maybe discuss with you more, maybe after the meeting or something, if possible.
Sure. Yeah. Okay.
Maybe other questions? Comments? Guillaume, please.
No, maybe I could still say that it will be better, I would say, to make topological the lower polariton branch rather than the upper one, as you did. Because, okay, it's maybe a very small detail because nothing is really topological there. But indeed, it was the same with this Karzik work. Excitons, they have their own dispersion, so then they become dark, but they exist, they are going at high energy, and they are resonant with this mode that you have in the middle. And this, well, even if you make photoluminescence or whatever, or nonlinear effects might start to be a problem. You will see really some effects. So okay, and even from a pure aesthetical point of view, it's better to be with the lower polariton branch so that these excitons, they are above and you have a real gap somewhere.
Okay, actually right now we're doing some more experiments with
but okay,
with different 2D materials, right, with WC2, and so we are trying actually to do exactly this. So we are trying to cross different bulk bands and see if topology appears in the lower polaritons. And actually we are doing this on purpose, right? We are trying to see nonlinear effects and so on, luminescence, valley polarization in our system, something which is this nice science work. They, I guess, demonstrated the valley polarization, because they use material which has very good valley polarization. Unlike us, our material, molybdenum diselenide, has very strong valley depolarization. So we still missing that, but we are trying to get there, right? So we are working on that.
Okay.
Thank you. I think that there is another question or comment from Tank Tan, and then we will probably conclude the session. Please.
Okay, sorry, just maybe one more a little comment on the valley polarization, because actually the circular polarization of the spin up, pseudo spin up or pseudo spin down states are in the far field. If you check the near field, you will find the near field, these two polarizations are actually mixed. So I think maybe you need to also consider that the near field, because when you have a 2D material, you have you want to integrate over all the circular polarizations on the space. So basically, the center of the cell.
So actually, if you look at our paper, so the supplement is twice longer than the paper itself. So, and we, I think, for the first time, detailed the mechanism of interaction of valley polarized excitons with near field. So if you look, we actually, in the supplement, on arXiv, there is supplement. We show that photons actually near field carry both spin and angular orbital momentum. So, and then both of these interact differently with excitons. Actually, one of them completely doesn't matter. So only spin really matters spin really makes difference with which value really these topological modes interact. So, but again, so we have the theory, but in experiment, we don't see this value polarization. We are working on that at the moment, right? So
yeah, I think it may not be, yeah, just from my experience, it may not be very easy to see, because actually at the center of the cell, you have one circular polarization, but at the edge of the cell, you have the other. So basically at near field, you have the mix.
yeah, you're
so,
saying it's not, it's highly inhomogeneous, right? So exactly, so it averages over the unit cell, right? Only the spin, what I'm saying. So what this really matters is the spin. So, but again, I don't know how you define the polarization, right? In the near field, there are several ways to do it, right? So again, I suggest, so I think the theory that we have in the supplement, you can look over, it should be correct. At least we have some other experiments where we show some non-reciprocity, which is photo-induced, and that shows that it should work that way.
Okay. Yeah, I would be very interested to maybe.
Yeah, sure. Yeah, just please send me an email and we can talk more. Right. I'm still reading your work, so still it will probably take a few more days for me to deeply really understand it. Okay. Thank you.
Okay. Thank you.
Okay. Thank you very much.